Introduction. Who is Sabine Hossenfelder, and why does she make physicists uncomfortable? In the quiet halls of academic physics, where polished chalkboards gleam with equations and conferences echo with cautious optimism, few voices ring as sharply as that of Sabine Hossenfelder. A theoretical physicist by training and a scientific iconoclast by conviction, she has made a name for herself, not by following the mainstream, but by relentlessly questioning it. Hossenfelder is not a crank. She's no outsider shouting at science from the margins. She holds a PhD in physics, has published peer-reviewed research on quantum gravity, and works at the Frankfurt Institute for Advanced Studies. Yet, in a field increasingly driven by abstract math, bold conjectures, and aesthetic elegance, Sabine has dared to ask a forbidden question. What if we're wrong? Her most famous work, Lost in Math: How Beauty Leads Physics Astray, reads like a manifesto. In it, she dismantles the quiet dogma that has crept into the foundations of physics. The belief that the universe should be elegant, symmetric, and mathematically beautiful. For decades, this belief has guided physicists toward ideas like supersymmetry, string theory, and multiverse cosmology. But what if this guiding principle has led science off a cliff? To Sabine, modern theoretical physics has become an echo chamber. Mathematically rich models are pursued not because they make accurate predictions or explain new data, but because they are beautiful. Experimental confirmation, once the gold standard of scientific progress, has taken a backseat. We are stuck, she says, and no one wants to admit it. This audiobook is not a biography. It's not even an endorsement. It's a journey into the mind of someone who believes that science has lost its way and has the courage to say so. We will explore her harshest criticisms, her boldest proposals, and the philosophical undercurrents that guide her thinking. You will not find comfort here. You will not hear about breakthroughs that change everything or genius theories that tie the universe in a neat bow. Instead, you'll be asked to rethink what science really is, how it should work, and whether the brightest minds of our time have wandered too far from the light of evidence. Because if Sabine is right, then physics isn't just lost in math, it's lost in itself. Let's begin. Chapter 1: The Myth of a Mathematical Beauty. For decades, physicists have been chasing beauty. Not the kind you find in art or poetry, but something colder. More precise, the kind etched into equations that loop with symmetry, balance, and elegance. In the minds of many scientists, beauty is not just aesthetic. It is a guiding principle, a compass, a signpost pointing toward truth. But what if it's a mirage? Sabine Hossenfelder argues that this obsession with mathematical beauty has not led physics toward greater understanding. It has led it into a dead end. In the 20th century, the most successful theories in physics, Einstein's general relativity, and the standard model of particle physics, were indeed elegant. Their mathematical structures were compact and symmetrical. Their predictions were astonishingly accurate. It was tempting to believe that beauty was truth, and truth was beauty. That belief, however, became dogma, and dogma is the enemy of progress. Hossenfelder reminds us that nature does not owe us beauty. The universe may be messy. It may be asymmetrical. It may be clumsy. If our theories are failing to match experimental data, perhaps it's not the universe that's wrong. Perhaps it's our expectations. Take supersymmetry, one of the most mathematically beloved theories. It was designed to fix problems in the standard model by adding a partner particle, restoring symmetry to the equations. It was beautiful, elegant, perfectly tuned, but it didn't show up despite billions of dollars poured. In two particle colliders like the Large Hadron Collider, LHC, no evidence of supersymmetric particles has been found. And yet, many physicists continue to cling to it. Why? Because it's beautiful. Because it should be true. Because it feels right. Sabine calls this what it is: wishful thinking dressed up as science. She draws a sharp line between mathematical aesthetics and empirical truth. In her view, a beautiful theory that makes no testable predictions is not superior to an ugly one that does. In fact, it's worse because it distracts from the real work of science, explaining the universe through observation, data, and falsifiable ideas. Some of her critics say she misunderstands the historical role of beauty. They point out that many scientific breakthroughs were first inspired by aesthetic intuition. Dirac's equation, for instance, predicted antimatter before it was observed. Doesn't that prove beauty works? Hossenfelder responds with precision. Yes, beauty can inspire discovery, but that doesn't mean it guarantees truth. Those examples are cherry-picked. For every success story, there are dozens of beautiful theories that led nowhere. The difference is that Einstein and Dirac lived in a time when data was king. They followed beauty, but they submitted it to reality. Today, the equation has reversed. Beauty leads, and reality is expected to follow. She warns that this reversal is not just a philosophical error, it's a practical danger. When researchers prioritize elegance over evidence, they risk building castles in the clouds. They write papers that impress peers, generate citations, and win grants, but contribute little to our understanding of nature. the field becomes insular, self-referential, and resistant to criticism. This is not science, she says. It's a culture, and cultures, like beliefs, can be wrong. In interviews and lectures, Hossenfelder has bluntly stated that physics has lost its way, not because we lack data, but because we've stopped listening to it. Theorists propose models with parameters too high to test, or concepts that cannot be observed in principle. These aren't just theories without evidence, they are theories without hope of evidence, all in the name of beauty. Her message is not to banish beauty from physics, it's to demote it, to return it to its rightful place as an occasional companion, not a master. A helpful guidepost, not a requirement. The role of beauty in science should be modest, skeptical, and always subordinate to what the universe actually tells us. As she writes, if you want your theory to be beautiful, that's fine. But if it doesn't match reality, it's not physics, it's art. In an age where physicists are taught to revere elegance as if it were proof, Hossenfelder dares to ask, what if nature simply isn't elegant? What if truth is ugly? And more importantly, are we brave enough to accept it? Chapter 2: String Theory and the Decades We Lost in the Grand Halls of Theoretical Physics. Few ideas have enjoyed such prestige, funding, and philosophical admiration as string theory. For over 4 decades, it has been the dominant candidate for a theory of everything, a framework to unify quantum mechanics and general relativity into one coherent, elegant, and mathematically complete model. Its equations shimmer with beauty. Its promise is immense. But according to Sabine Hossenfelder, it's a promise that has not been kept. String theory posits that the fundamental building blocks of the universe are not zero-dimensional point particles, but one-dimensional strings that vibrate at different frequencies. Each vibrational pattern corresponds to a different particle. This idea naturally includes gravity, which is why many physicists saw it as the key to quantum gravity, the holy grail of theoretical physics. It sounds revolutionary, but here's the catch. String theory does not make unique predictions. It is not falsifiable. It has not explained any new data. And most disturbingly, after more than 40 years of development, still has no experimental confirmation of any kind. Hossenfelder is blunt. She calls string theory a mathematical indulgence, a beautiful, self-contained playground where physicists can spend careers tweaking equations, calculating higher dimensional spaces, and exploring abstract symmetries, all without confronting the reality of nature. String theory is not science, she has said. It's mathematics with a hope attached. At the heart of her critique lies a simple principle. Science advances by confronting theories with data. But string theory has evolved in precisely the opposite direction. As it grew more complex, it developed what physicists call the landscape problem, a proliferation of possible solutions. Instead of yielding one unique universe like ours, string theory allows for up to 10,500 different universes, each with its own physical laws. This is not a theory of everything. It's a theory of anything. In response to this ambiguity, some string theorists embraced the idea of the multiverse, a vast ensemble of universes, each corresponding to a different solution of string theory. Our universe, they argue, is just one bubble in an eternal cosmic foam. That might be true. But there's a problem. We can't test it. We can't observe other universes. We can't verify their existence. So the question arises, if it can't be tested, is it still physics? Hossenfelder's answer is clear. No, she's not alone in this view. Even some prominent physicists within the string theory community have expressed concern that the field has become more metaphysics than physics. But while many whisper doubts, Hossenfelder shouts them. She has written blogs, given lectures, and appeared in interviews around the world, calling out the field's failure to deliver on its promises. What makes her critique so piercing is not just the substance, it's the timing. The world has invested heavily in particle physics infrastructure. Billions have been spent on colliders like the LHC, partly justified by the hope that they would find evidence of string theory or its relatives, like supersymmetry. They didn't, and yet string theory continues to dominate the academic landscape. Why? Because, Sabine argues, the field has become self-perpetuating. PhD students write dissertations on string theory because their advisors did. Funding agencies grant support to string theory because it's well established. Journals publish string theory papers because they're familiar. The theory survives not because it works, but because it has institutional inertia. This is not how science is supposed to function. Hossenfelder does not claim that string theory is wrong. Her critique is deeper, that string theory is untestable, and that this should disqualify it from being called physics. If a theory cannot be falsified, it cannot be corrected. And if it cannot be corrected, it cannot improve. It becomes a belief system, elegant, coherent, and entirely detached from reality. One of her most controversial claims is that the dominance of string theory has actively harmed physics by monopolizing resources, talent, and attention. It has crowded out alternative approaches to quantum gravity, many of which, she argues, might have been more fruitful. In other words, the problem is not just that string theory failed to succeed, it's that it prevented success elsewhere. Imagine if all of biology had bet on one theory of evolution for 40 years and it turned out to be wrong. That is the situation Sabine sees unfolding in physics. She does not oppose bold ideas. She supports speculation when it's tethered to reality. What she opposes is mistaking mathematical beauty for empirical truth and allowing an untestable framework to define an entire field. That, she believes, is a betrayal of science itself. As she puts it, we didn't solve the problems, we just renamed them. The tragedy is not that string theory is false. The tragedy is that it may be irrelevant, and we may have spent the better part of a generation chasing an illusion. Chapter 3: The Multiverse Delusion. There's something undeniably seductive about the idea of a multiverse. A cosmos not limited to a single universe like ours, but a vast, perhaps infinite, collection of parallel universes, each with its own laws of physics, constants, and cosmic history. In one, you were never born. In another, gravity is stronger. In a third, Earth never formed. It sounds like science fiction, and in many ways, it is. Yet in modern physics, the multiverse is treated with surprising seriousness. Once confined to fringe speculation, it now appears in mainstream journals, popular science books, and even Nobel Prize speeches. The multiverse has become a centerpiece of theoretical cosmology. Sabine Hossenfelder calls this development not just speculative, but delusional. Her criticism is as bold as the idea itself. The multiverse is untestable, unfalsifiable, and unnecessary, a fantasy propped up by failed theories and lazy reasoning. And worse, it violates the most sacred principle of science, that it must be anchored in evidence. So where did this idea come from? There are several versions of the multiverse, each born from a different corner of theoretical physics. One arises from cosmic inflation, the idea that the early universe expanded exponentially fast, creating pocket universes with different physical conditions. Another stems from string theory's landscape problem, which permits 1/500 possible solutions, each representing a different universe. A third comes from the many worlds interpretation of quantum mechanics, where every quantum event spawns a new branch of reality. Each of these multiverse proposals attempts to solve real problems, but in Sabine's view, they create a much bigger one. They abandon science's requirement for empirical validation. If these other universes cannot be observed, even in principle, then how are they different from metaphysical speculation? How is this physics and not philosophy masquerading in mathematical robes? Proponents of the multiverse argue that even if we can't see other universes directly, we can infer their existence. For example, if a theory that predicts a multiverse also makes accurate predictions about things we can observe, like the cosmic microwave background, then perhaps it gains legitimacy. But this reasoning is shaky, Sabine argues. Most multiverse theories are so flexible that they can accommodate any data. They are not predictive, they are post-dictive. They explain whatever happens after it happens. That is not a scientific theory. That's a coping mechanism in public lectures. Hossenfelder is unrelenting. If your theory explains everything, it explains nothing. She warns that the allure of the multiverse is not based on evidence, but on convenience. When the data doesn't match your model, blame another universe. When fine-tuning looks improbable, say, "We got lucky in the multiverse lottery." This line of reasoning is not just unscientific. She says it's intellectually dishonest. One of the most common justifications for the multiverse is the so-called anthropic principle, the idea that we observe a universe compatible with life because otherwise we wouldn't be here to observe it. While logically correct, Sabine finds this deeply unsatisfying. It amounts to giving up on understanding why the laws of nature are the way they are. Instead of finding mechanisms, we shrug and say, "It just happened to be this way." She compares it to discovering a perfectly tuned machine and assuming that there are countless broken ones elsewhere. Rather than asking how it was built, Hossenfelder's deeper concern is cultural. The multiverse, like string theory, represents a shift in physics from the testable to the abstract, from the empirical to the ideological. Theoretical physicists are no longer constrained by what can be measured. They're chasing what can be imagined, and imagination is infinite. This shift has real consequences. When untestable ideas gain traction, they draw attention, funding, and talent away from testable science. They distort the public's understanding of what physics is and what it is not. They encourage a dangerous trend, redefining success. In physics, not by contact with reality, but by elegance, consistency, and peer approval. Sabine doesn't hate the multiverse. She hates what it represents: a failure of discipline, a loss of humility, a willingness to trade the hard work of science for the easy comfort of explanation without prediction. To her, the multiverse is not a discovery, it's an excuse. And in making excuses, physics is betraying its most fundamental duty: to explain the universe we actually live in, not the infinite ones we can't. Chapter 4: Science by Popularity. How theories survive without evidencing a field defined by its rigor. One would expect that only the strongest ideas, those supported by data and predictive power, rise to the top. But Sabine Hossenfelder paints a very different picture. In her eyes, modern theoretical physics often resembles a popularity contest. where theories survive not because they work, but because they're fashionable, peer pressure, institutional inertia, and academic prestige. These, she argues, now shape the direction of research more than experimental validation ever could. It's a startling claim, and it cuts to the core of how science is supposed to operate. Imagine you're a young physicist entering the world of academia. You want to work on quantum gravity or cosmology, but you're quickly told, either explicitly or through the reward structures around you, that your best chance of success is to work on what's hot. String theory, multiverse cosmology, supersymmetry. These fields dominate the conferences, the journals, the grants. If you choose to work on alternative ideas, theories that challenge the status quo or explore untested possibilities, your chances of getting published, funded, or hired drop dramatically. This, Sabine says, is how scientific monocultures are born. In a truly healthy scientific ecosystem, a diversity of ideas would compete on equal footing. Theories would rise or fall based on their ability to explain the natural world. But in physics, today, Hossenfelder sees a closed loop of validation. Theories become popular. That popularity brings more students and researchers. More researchers publish more papers. Those papers reinforce the theory's prestige, attracting more funding. And the cycle continues. Evidence becomes optional. Reputation becomes essential. Sabine compares this to a feedback loop, not of data, but of social approval. Theories that align with existing narratives are rewarded. Theories that challenge the consensus are marginalized, often without fair evaluation. Even worse, she argues, physicists rarely admit this reality. Instead, they convince themselves that the most popular theories are also the most promising, without recognizing the bias that popularity introduces. She calls it the groupthink problem in science. Hossenfelder doesn't believe this situation emerged out of malice. She knows that most physicists are intelligent, well-meaning people. But, like any human community, science is vulnerable to tribalism, prestige dynamics, and fear of professional isolation. Challenging dominant ideas carries social and career risks, especially for early career scientists, and so many stay silent, or conform, or learn to rationalize. If you criticize string theory too loudly, she said, you won't get invited back to the conferences, and without those, your career stalls. This pressure to conform creates a chilling effect. Bold ideas are filtered out not by experiments, but by the invisible hands of gatekeeping and professional etiquette. As a result, physics becomes stagnant, repeating the same calculations, repackaging old assumptions, avoiding confrontation with failure. And yet, failure is everywhere. EASUPERSY, not found. Extra dimensions, undetected. Multiverse, unobservable. Decades of research have yielded little more than elegant papers and complex models with no empirical confirmation. But instead of reassessing these ideas, the field doubles down. The failure to detect predicted phenomena is often met not with revision, but with reinterpretation. It's still a good theory, they say. We just need more energy, more precision, more time. Sabine calls this scientific inertia, the inability of a field to turn away from its preferred narrative, even in a face of mounting disappointment. This doesn't mean that all popular theories are wrong. But popularity should not be mistaken for validity. And in a discipline that prides itself on skepticism, the lack of internal criticism is troubling. One of the most dangerous aspects of this culture, she warns, is its effect on progress. When everyone works on the same thing, group biases are amplified, the blind spots grow, and truly revolutionary ideas, the kind that once defined physics, are lost before they begin. She urges young scientists to resist the pressure to conform, to be skeptical of what's fashionable, to remember that science is not a democracy. Truth is not decided by votes, citations, or prestige. It is decided by nature. And nature doesn't care what's popular. If physics is to move forward, it must rediscover its courage, the courage to ask uncomfortable questions, challenge sacred cows, and reward intellectual risk. Not just professional safety, because science, by popularity, is not science at all. Chapter 5. The Crisis in Quantum Gravity. What we're not talking about. Quantum gravity. The phrase alone conjures images of deep space, black holes, and the edge of time itself. It's the frontier of theoretical physics, the elusive unification of general relativity, Einstein's theory of gravity, with quantum mechanics, the framework that governs subatomic particles, a union of the large and the small, the smooth and the chaotic, order and probability. It should be the most exciting area of modern science. But Sabine Hossenfelder sees something else, a field in quiet crisis. For decades, physicists have tried to bridge the gap between gravity and quantum theory. From string theory to loop quantum gravity to causal dynamical triangulations, brilliant minds have proposed intricate models, elaborate mathematics, and even entirely new concepts of space and time. Yet, after all this effort, the result is painfully clear. We have no working theory of quantum gravity, and more disturbingly, we're not even close. Hossenfelder doesn't blame the difficulty of the task. Everyone agrees it's hard. she blames the way the problem is being approached. In her view, quantum gravity research has become too detached from experimental reality and too consumed by theoretical aesthetics. It's no longer a search for truth. It's a battle of ideologies. One of the first red flags, she says, is that physicists don't agree on what they're even trying to achieve. What exactly is quantum gravity? Should it quantize space-time itself? Should it emerge from something more fundamental? Should it be a field theory or a geometrical construct? There is no consensus, only camps. Each group champions its own approach. String theorists claim that tiny vibrating strings are the answer. Loop quantum gravity advocates believe that space is made of discrete chunks. Others suggest space-time is emergent, that it's not fundamental at all. The variety is impressive. The progress is not. Sabine argues that this fragmentation reflects a deeper problem. We're theorizing in the dark. None of the models are strongly constrained by data. There are no experiments capable of testing their core predictions. So theorists are free to invent, extrapolate, and decorate their frameworks without fear of contradiction. It's not just that we don't know which theory is right. We don't know if any of them are even in the ballpark. She likens it to a ship lost at sea, guided not by stars, but by internal maps that may or may not correspond to reality. Worse still, the community rarely confronts this impasse. In public, optimism reigns. New conferences are held. Grants are awarded. Papers continue to pour out, often repeating the same ideas in slightly different forms. But privately, many physicists admit frustration. The field is stuck, but no one wants to say it out loud. Sabine says it out loud. She believes the crisis in quantum gravity stems from a refusal to question assumptions. For example, should gravity really be quantized? It's taken as a given, but why? Every other force has a quantum description, but gravity might be different. Maybe it resists quantization for a reason. Maybe trying to force it into the quantum mold is the wrong move altogether. Another assumption she challenges is that space and time are fundamental. What if they're emergent phenomena, macroscopic illusions arising from something more basic, like temperature or pressure? If that's true, then trying to quantize space could be as misguided as trying to quantize a wave in a stadium crowd. You're quantizing the wrong thing. These are uncomfortable questions. We escape the current stalemate. She also calls for a return to empirical roots. Some argue that quantum gravity is simply beyond experiment, that the relevant energies are too high, the scales too small. But Hossenfelder pushes back. Maybe we've been looking in the wrong place. Maybe clues lie not in black holes or the early universe, but in anomalies at lower energies, subtle deviations in gravitational behavior, Q, tiny effects in quantum systems, unexpected signals in precision measurements. It's not glamorous, but it's testable. Her message is clear. The crisis in quantum gravity is not a lack of intelligence or imagination. It's a lack of constraint. We've created a playground of possibilities without the discipline of observation. And without that discipline, science loses its compass. The tragedy is that quantum gravity is too important to drift endlessly. Understanding it isn't just about satisfying curiosity, it's about answering foundational questions. Time. What happens inside a black hole? We may not know the answers, but Sabine reminds us that we won't find them by pretending progress is being made when it isn't. We won't find them by rewarding conformity, ignoring failure, or chasing beauty. We'll find them by returning to what made physics great: evidence, skepticism, and a willingness to admit when we're lost. Chapter 6. The Bias Beneath the Lab Coat. How scientists fool themselves. Science is often presented as the purest expression of human reason, a method immune to bias, built on logic, data, and a pursuit of truth. As detached observers, guided solely by evidence, untouched by emotion or ego, Sabine Hossenfelder doesn't buy it. In her view, this image is not only inaccurate, it's dangerous. Because when scientists convince themselves that they are free of bias, they become blind to how deeply it shapes their thinking. Bias doesn't wear a lab coat. It doesn't need to. It sneaks in quietly, through assumptions never questioned, models never doubted, and groupthink never challenged. It lives in the way problems are framed, how theories are interpreted, and which questions are even allowed to be asked. And it thrives in the unspoken hierarchies of academia, where seniority and prestige often overshadow critical inquiry. Hossenfelder argues that physicists, like all humans, are prone to cognitive distortions, chase elegant solutions because they feel right. They prefer theories that align with their past work. They interpret ambiguous data in ways that confirm their beliefs. These are not moral failures. They're neurological defaults. The problem isn't that scientists are biased. The problem is that they pretend they're not. Take confirmation bias, the tendency to seek and value evidence that supports what we already believe. In physics, this can manifest subtly. A theorist might tweak a model just enough to align with current data, then declare success even if the model lacks predictive power. Experimentalists might dismiss anomalous results as noise if they contradict accepted theories. These decisions aren't malicious. They're human. But left unchecked, they erode the objectivity that science depends on. Then there's the status quo bias, the preference for established ideas and institutions. In academia, young scientists are often encouraged to stand on the shoulders of giants, but rarely to question whether those giants were standing in the right place to begin with. Sabine sees this in the dominance of string theory and multiverse cosmology. Once these ideas became entrenched, they gained a momentum that had little to do with merit and everything to do with social dynamics. Career pressures amplify the problem. Getting a position in academia depends on publishing, frequently in prestigious journals, aligning with influential research groups, and securing grants from conservative funding bodies. None of this rewards intellectual risk. It rewards conformity, polish, and the appearance of productivity. The result, Sabine says, is a generation of physicists trained more to survive than to challenge. And yet, many scientists remain convinced that the scientific method protects them. They point to peer review, replication, and rigorous training. But Hossenfelder argues that these mechanisms, while important, are not immune to the same biases. Peer review often reinforces groupthink, favoring familiar methodologies and fashionable topics. Replication is rare in theoretical physics, where many models can't be tested. And rigorous training often means learning to think within a very narrow box. Sabine isn't cynical about science. She believes in it deeply, but she insists that science must recognize its own fallibility. The myth of objectivity doesn't protect the scientific process. It blinds it. So what can be done? First, she calls for greater transparency. Physicists should be more honest about the assumptions in their models, the flexibility in their equations, and the subjective decisions that shape their work. They should stop pretending that theories are purely derived from data, and admit how often intuition, preference, and aesthetic bias play a role. Second, she advocates for institutional reform. Funding bodies and academic departments should reward intellectual diversity and methodological dissent. Young researchers should be supported when they question orthodoxy, not punished. The structure of science must allow space for uncomfortable ideas, not just convenient ones. Third, she suggests that scientists engage more with philosophy. Many physicists scoff at philosophy as irrelevant, but Hossenfelder sees that attitude as part of the problem. Philosophy teaches us to examine our assumptions, to question definitions, and to clarify concepts. These are not distractions. They are essential tools, especially in fields like quantum gravity, where so little is known. Ultimately, Sabine's message is not that scientists are flawed, but that science is human. And if we want it to remain the most powerful tool for understanding reality, we have to treat it like any other tool, maintain it, sharpen it, and use it with awareness, because when scientists fool themselves, it's not just their theories that suffer, it's the truth itself. Chapter 7: Physics or Performance. The spectacle of modern science. It starts with a headline. A new theory could explain everything. Physicists say we may be living in a multiverse. Scientists prove time may not exist. These kinds of titles are everywhere, on news sites, in viral videos, even in glossy magazine covers. Physics, once the most austere of disciplines, has become show business. And Sabine Hossenfelder is not impressed. She calls it the spectacle of science. A growing tendency within the scientific community to present theoretical speculation as profound revelation, and to embrace media attention not as a consequence of discovery, but as a goal in itself. In her eyes, physics is no longer just a search for truth. It's a performance. Hossenfelder isn't criticizing science communication itself. She supports public outreach. And she has her own YouTube channel with hundreds of thousands of followers. What she criticizes is the blurring of lines between speculation and science, between honest inquiry and entertainment, between ideas that are tested and ideas that are simply marketable. She has a word for it: science fiction with equations. The problem, she argues, begins within the scientific community itself. Physicists, eager to stand out in a competitive academic environment, often inflate the implications of their work. A paper that tweaks an existing equation is framed as a potential breakthrough. A model with speculative assumptions is portrayed as a step toward unification. The language becomes grandiose, the claims ambitious, and the caveats buried deep, if included at all. From there, the media picks it up. Journalists, not trained in the nuances of theoretical physics, translate technical jargon into sweeping statements. And scientists, far from correcting these simplifications, often welcome the attention. Fame boosts their profiles, helps with grants, and builds public prestige. Everyone wins, except the truth. Hossenfelder sees this as a betrayal of science's core mission, not because scientists want to lie, but because they've become too comfortable with ambiguity. They've stopped asking, "Is this true?" and started asking, "Will this get attention?" This dynamic becomes especially dangerous when speculation is confused with evidence. Take the multiverse again, or string theory. These are frameworks that are mathematically consistent, but not empirically verified. Yet they are often presented to the public as established parts of physics, creating the illusion that the field has answers it doesn't have. The result is a distorted public perception, one where Physics seems to move from mystery to mystery, constantly on the brink of revolution, yet never delivering anything testable. This erodes trust. It also creates a sense of fatigue. If every week brings another mind-blowing theory, people eventually stop caring. Even worse, the spectacle affects how science is done. Funding agencies, influenced by public excitement, may prioritize flashy ideas over slow, careful investigation. Universities, eager to showcase cutting-edge research, promote the work of their most idea-savvy faculty. Young scientists, seeing what gets rewarded, shift their focus toward theories that promise fame, not necessarily insight. Sabine believes this feedback loop must be broken. She urges scientists to resist the temptation to oversell, to be honest about the limits of their work, to distinguish clearly between what is known, what is hypothesized, and what is purely speculative. This is not about being dry or boring. It's about respecting the audience, trusting that people can handle complexity, uncertainty, and even disappointment. She also encourages the public to be more skeptical, to ask better questions. What evidence supports this claim? Is this theory testable? How does it compare to alternatives? The more science is treated like entertainment, the more vital critical thinking becomes. And perhaps most importantly, she reminds us that science doesn't have to be spectacular to be meaningful. Real progress often happens quietly in the slow accumulation of data, in the refinement of models, in the patient correction of errors. That may not make for viral headlines, but it's how knowledge grows. Sabine's stance is not anti-communication. It's anti-hype, anti-hollow spectacle. She wants physics to inspire, but with substance, not illusion. Because, in the long run, the credibility of science depends not on how loudly it speaks, but on how honestly it listens. And if we reduce it to performance, we may one day forget what it meant to discover anything at all. Chapter 8: Why Physics Needs Philosophy and Why Physicists Hate It in the Modern Culture of Physics. Few things are dismissed as swiftly or with as much pride as philosophy. Philosophy is useless. Philosophy is for people who failed math. Physics has outgrown philosophy. These are not just internet quips. They're sentiments echoed by respected physicists, Nobel laureates, and public science communicators. Philosophy, they say, is outdated, a relic from a time before we had equations, data, and particle accelerators. Now, we don't need vague arguments about reality. We have models. We have math. Sabine Hossenfelder disagrees forcefully in her view. The disdain for philosophy within physics is not only ignorant, it's dangerous, because many of the problems that plague modern theoretical physics are not mathematical or technical. They are philosophical at their core. What does it mean for a theory to be real? What counts as an explanation? What is the role of simplicity, beauty, or naturalness in science? What is a law of nature? These are not scientific questions. They are philosophical ones. And ignoring them doesn't make them disappear. It just ensures that physicists address them poorly. Or not at all. Sabine argues that much of the confusion in modern physics, from the obsession with beauty to the proliferation of untestable theories, arises from unexamined philosophical assumptions. The belief that a simpler theory is more likely to be true, for instance, is not a law of nature. It's a metaphysical claim, inherited from centuries of philosophical tradition. But while philosophers are trained to identify, question, and analyze such assumptions, physicists often take them for granted. They build elaborate models on shaky, conceptual foundations, confident in the math, but blind to the meaning. She finds this intellectually lazy. Hossenfelder is not alone in this critique. Throughout history, many of physics' greatest breakthroughs were deeply philosophical. Newton invented a new concept of space and time. Einstein redefined simultaneity and causality. Bohr and Heisenberg grappled with the meaning of observation itself. These were not purely technical achievements. They were philosophical revolutions. So why the hostility today? Sabine believes it's cultural. As physics became more specialized and technical, its practitioners began to prize precision and predictability over reflection and introspection. Philosophy was seen as vague, slow, and detached from experiment. Physics became synonymous with hard data and hard truth. But this image is misleading, especially now. Many of today's most prominent theories, from string theory to multiverse cosmology, make few testable predictions. They are built on speculation, interpretation, and conceptual extrapolation. In other words, they operate in philosophical territory, whether physicists admit it or not. The irony, Hossenfelder points out, is that many physicists are doing philosophy badly, all while ridiculing it. She recounts how some theorists invoke Occam's razor, the idea that simpler explanations are better, without acknowledging its philosophical origins or limitations. Others talk about naturalness or elegance as if these were empirical properties rather than subjective aesthetic judgments. The result is confusion. Debates that masquerade as scientific disagreements are often philosophical at heart. And without the tools to navigate those debates, physicists resort to shouting matches, tribalism, and appeals to authority. Sabine calls for humility. She doesn't suggest that physicists become philosophers, but she does argue that they need to be philosophically literate. They need to understand the conceptual scaffolding of their work, not just its equations. Because when physics ignores philosophy, it risks mistaking assumptions for facts, models for reality, and speculation for truth. She also calls on philosophers to engage more seriously with physics. Too often, academic philosophy remains aloof from the sciences, focused on internal debates that seem disconnected from the real questions driving research. A productive dialogue requires effort on both sides. At its best, philosophy can act as a mirror revealing the hidden biases, circular reasoning, and unsupported claims that even brilliant minds can fall into. It reminds us that science is not just about calculation, but about meaning. Not just about prediction, but about understanding. In an age where physics risks drifting into abstraction, Hossenfelder believes that philosophy can help bring it back to earth, not by answering the questions, but by making sure we're asking the right ones. Chapter 9. Naturalness is dead, and we should let it go. For decades, theoretical physicists have been guided by a principle that sounds almost spiritual in its simplicity. Nature shouldn't require fine-tuning, a constant or parameter. In a theory has to be set with extreme precision to make the model work. If, for example, changing it slightly would destroy the entire universe, then something must be wrong. The theory must be incomplete. The universe, it is assumed, must be natural. This idea, called naturalness, has shaped some of the most ambitious projects in modern physics. It motivated the search for supersymmetry, the expectation of new particles at the LHC, and the belief that the standard model is just an effective theory hiding something deeper. But Sabine Hossenfelder says it plainly. Naturalness is not a law. It's a superstition. The principle of naturalness is not derived from data. It's not mathematically necessary. It's not even empirically successful. It's a belief, one that has failed over and over again. Take the Higgs boson. For example, according to the standard model, the mass of the Higgs particle should be subject to enormous quantum corrections. Left uncorrected, those corrections would make the Higgs mass astronomically large, far beyond what we observe. To make the numbers work, you have to fine-tune the Higgs mass to cancel out those quantum contributions with extraordinary precision, about 1 part in 1032. That's unnatural, physicists said. And so, they invented mechanisms to protect. The Higgs supersymmetry was supposed to solve this. So was Technicolor. So were extra dimensions. All of these models aim to make the Higgs mass natural. And yet, the Large Hadron Collider found the Higgs and nothing else. No supersymmetric particles, no new physics. Just the Higgs, sitting quietly at 125 GeV, exactly where the standard model said it would be, despite the enormous fine-tuning supposedly required. So what happened? According to Sabine, the problem wasn't with the data, it was with the expectation. Physicists assumed that naturalness was a legitimate guide, a signpost pointing to deeper truths. But it wasn't. It was a metaphysical preference, a philosophical aesthetic, and the universe didn't care. She puts it bluntly, nature is not obligated to conform to our sense of what's natural. Naturalness was always an assumption. And like many assumptions in physics, it was adopted because it worked until it didn't. The proton mass is natural. The electron mass is natural. So, when the Higgs appeared to require fine-tuning, physicists assumed a fix was around the corner. They built entire careers on that assumption. They published papers, got grants, built detectors, all in service of a principle that had never been tested and never earned its place as a foundation of science. Now, Sabine says, it's time to let it go. Not because it's aesthetically displeasing, but because it's empirically bankrupt. She doesn't claim that fine-tuning problems aren't real, only that we may be thinking about them in the wrong way. Maybe fine-tuning is just how the universe works. Maybe parameters that appear unnatural to us are just facts of reality. Or maybe our models are incomplete in ways we haven't even begun to understand. The danger of clinging to naturalness, she argues, is that it narrows our imagination. It tells physicists which ideas are reasonable and which are ugly. It biases funding decisions, publication standards, and research trajectories. It creates a culture where ideas are judged not by their explanatory power, but by how comfortable they feel. And comfort is not science. Sabine goes further. She believes that the insistence on naturalness has actively delayed progress by funneling attention towards certain natural models and away from others. It has distorted the field. Worse, even after its predictions failed, many physicists still cling to it, rebranding their theories or shifting the goalposts. She compares this to theology, not because it's irrational, but because it's dogmatic science. She insists must be willing to change course when evidence demands it. And the evidence is clear. The universe does not behave the way the principle of naturalness predicted. The models it inspired have failed to describe reality. And so, Sabine says, it's time for physics to grow up. It's time to stop expecting the universe to be simple, symmetric, or aesthetically pleasing. It's time to accept that our preferences, our human notions of beauty, elegance, and naturalness may be irrelevant to how the world actually works. Because science isn't about what we want to be true. It's about what is true, no matter how strange, awkward, or unnatural it may seem. Chapter 10: The Future of Physics. If we dare to change. Theoretical physics once stood at the frontier of human knowledge, fearless, disruptive, and revolutionary. It gave us relativity, quantum mechanics, and the very structure of the universe. But according to Sabine Hossenfelder, the field now risks collapsing under the weight of its own stagnation. Not because we lack intelligence, not because we lack tools, but because we lack honesty in this final argument. Hossenfelder brings together the threads of her critique, the worship of mathematical elegance, the drift toward untestable speculation, the dominance of groupthink, the corruption of incentives, and the dismissal of philosophy and critical reflection. These aren't isolated issues. They are symptoms of a deeper problem, one that threatens the future of physics itself. She calls it science without self-awareness. Physicists, she says, have become too comfortable in their institutions, too insulated by prestige, too seduced by their own narratives. They mistake complexity for depth, citations for truth, and consensus for correctness. They build elaborate castles in the mathematical sky, forgetting to check if the ground beneath them even exists. And when the castles collapse, as many already have, they simply move on to the next elegant distraction. Sabine isn't saying the work should stop. She's saying it should change, and she offers a vision of what that change might look like. First, it means returning to testability as a non-negotiable standard. Theories must make predictions. Models must risk falsification. If a framework cannot, in principle, be tested, not today, but ever, then it belongs in philosophy, not physics. Second, it means questioning assumptions that have calcified into dogma. Not all fine-tuning requires fixing. Not all mathematical beauty points to truth. Not all old ideas deserve protection. Progress demands discomfort. Third, it means rethinking how physics is structured. The current reward systems, grant funding, publication pressure, institutional politics encourage safe thinking and penalize boldness. That must change. We need structures that promote dissent, protect intellectual risk, and support curiosity. That doesn't fit the mold. Fourth, it means inviting philosophy back to the table. We need clarity of thought, precision of language, and conceptual rigor, not just algebraic cleverness. When we ask, what is time, or what is reality, we are doing philosophy, whether we admit it or not. Better to do it well. Finally, and perhaps most painfully, it means accepting that we may not be close to a final theory. The universe may not give us neat answers. It may not simplify. It may not conform to our deepest intuitions. That doesn't mean we give up. It means we grow up. Sabine Hossenfelder doesn't claim to know what the future of physics looks like. But she knows what it shouldn't look like. A stage play of certainty, while truth hides in the wings. If physics is to rediscover its power, to truly confront the unknown, it must let go of its illusions. Illusions of inevitability. Illusions of progress without risk. The future of physics is still unwritten, but it will not be written by those who protect what is comfortable. It will be written by those who question what is sacred, if we dare. A call to courage and curiosity as we come to the end of this journey through the ideas and critiques of Sabine Hossenfelder. It's clear that physics stands at a crossroads. The path ahead is uncertain, cluttered with unanswered questions, failed expectations, and uncomfortable truths. But it is also full of possibility. Change is never easy. It demands humility to admit where we've gone wrong. It demands courage to challenge the comfortable consensus. It demands curiosity to explore new directions without that safety net of certainty. Sabine's challenge is not just to physicists, but to all of us who seek to understand the universe, to reclaim science as a disciplined, honest, and open-minded pursuit, to embrace complexity without surrendering to confusion, to dream boldly but ground those dreams in reality, because, in the end, the beauty of science is not in elegant equations or dazzling theories. It is in its relentless commitment to truth, wherever that truth may lead. May we have the courage to follow.